Hello everyone, welcome to Adhyap. I'm Leena with you and this is my sister.
This is Hannah with you, and today we're here to talk about the least squares cost function, which is mainly used for calculating the magnitude of error in your predicted values and your actual value. So, this mainly is used in linear regression because it relies on a function called the hypothesis function, which calculates these predictions. But since the hypothesis function isn't that accurate, we need to use the least squares cost function. So right now, Leena will explain what is the least squares cost function and how does it help in linear regression.
Well, linear regression can be shown as a graph. Actually, we talked about linear regression in our last video, which was about hypothesis function. But I'll talk a little more about it. So these are data points, and each data points are prediction y hat, and this is our regression line. So here in our data point and our regression line, we want to get our data points close to the regression line. Why? Because we want to go to the place where the good predictions are, which is our regression line. So there's a distance between the y and y hat, as you can see. This is the error between our target variable y. So what we need to do is calculate this error, and then this error will be taken to another function called gradient descent,
which will solve these issues.
Yes. So this is where the area of least squares cost function goes.
Okay, so I'd first like to add something before we get to the equation, that we used to write in the coordinate wise that the vertical wise it's y and horizontally it's x, but it can also get confused since the regression line y is also written and known as y, so we can get confused with this, which is why we also use the word alpha from the Greek alphabet to represent the coordinate y and the Greek alphabet beta to represent x. So these are some basic things you need to know on this. So now I'll move on to the equations.
So you can see that Hannah just put j. Well, we can change this to any other letters. It doesn't really matter, but it's really changed. And theta will be our weights. Actually, we need this for our summation n. And n by 2 is our batches. So we'll be separating our data set so it doesn't get heavy on the model while training. And n will be having the number of thetas. Why? Because we want to iterate depending on the number of thetas, because that's having our x. And as we need a y hat, we need the theta as well.
Okay, so these are basically known as our hyperparameters or weights, and then we use 1 by 2 to get different batches, like different units in a specific subject. Each unit may be containing numerous chapters, and when your model goes through one unit, you need to ask questions to know whether they understood everything from that unit, right? So that's basically what they're doing right now, and we want to start from the beginning so we can capture everything, like validating, or the step in between the training that will check whether our model knows everything and is ready to go to the next batch or next step. And then our n will extract all of our weights, right? We might have numerous numbers of weights, right? And this is big summation to add all the values in calculation. And I relies on n to get the number of weights. So basically it will go through each of the weights and do this calculation. So this calculation is pretty simple, And you may be thinking, we're using the hypothesis function here, and what is this? Actually, this can also be written as y hat. Now I suppose it's easy. Actually, the hypothesis function is also known as y hat because it makes the output prediction, right? So this is why we can also use y hat here, but now we have to get the iterations of that because of the weights. So in this scenario, it will be like this, right? So we covered that, and the basic logic here is that we got to minus our prediction and our actual value or real value, ground truth, right? So now we will get the difference between this, right? And definitely there will be a difference between the y and the y hat, right? If there's an error. And if there isn't, then the value will be 0. Now moving on to the square. So the square is basically just to make this entire calculation to a percentage. So for example, let's say after adding each of these errors together, we got the number 5. Now from this, if we squared, we would get a result of 25%. And that's basically how it works. And this would be the answer. So when we actually do in real scenarios, it might be more simpler than you think it is. So we'll move to the scenario. Okay. So let's say we have a dartboard and Lena isn't that perfect and she's hitting everywhere. So we'll say that there are 5 rings in this.
So each of the wings will be as a measurement, right? And each of them, one dart will be there. Each dart we have to take. So it will go like this, 1, 2, 3, 4, 5. So the bullseye is where we are hitting. That's our regression line over here. And our darts are y hat, our data points.
Or the predicted values. But now let me show you the values. So our data point 1 may be not that good and it reached here, very far from the point or the place we're trying to reach, but we're just started, right? So this is 1. We're counting from this way because we want to get the calculations for the error, right? To make you understand. So this will become 1 and this will become D2, which will be, let's say, maybe better. It reached in our 3rd ring. So this is our 3rd ring. And D3, even better than that. And it reached the 4th ring. And the 5th one is our bullseye. So now we got these values. So these are our positions. Now what we need to do, we need to minus it with the actual value. Since there are 5 values here, we need to subtract them with these values.
So actually the error will be taken now and then it will be sent to the gradient descent. So let's say, as Hannah previously told, we got 25%. That will be sent to the gradient descent. Depending on that error, the gradient descent will tune our hyperparameters, which runs the hypothesis functions, and it will fix the model.
Okay, so now we subtracted all these values with our total number of rings, right? And now we got these errors, right? Now our job is to square them and add them together, right? So square 4, add with 2 squared.
So we'll be squaring all of these, as first of all, sometimes we can get negative values which we won't show you here, but in our regression line, if it comes down, then it means this will be a negative value. So that's another reason why we are squaring.
Yeah, most of the time maybe it will come that way because we are minusing first, subtracting first our predicted values with the y. So if there's an error, then most likely it won't work, right? That wise, yeah, it can come. So now we'll show you how the actual way of the percentages and addition will work. So 4 squared will become 16, 2 squared will become 4, so 20, and 1 squared will become 1. So the answer is 21%. So this is our answer. But of course there are many other ways to represent this. Like Lena told, there are 2 other ways that may be most popular, which is RMSE, root mean squared error, and MAE, mean absolute error, right? And these may be the most popular that you see. But this only calculates the number of errors, but doesn't really fixes it, which is why the most important function that you will see anywhere in linear regression will mostly be gradient descent. So you got to be more detailed onto gradient descent. Okay, so I think it's time to wind up. So if this video helped you, then don't forget to follow, like, and click the bell icon for real-time updates. If you want to contact us, then our email IDs and all will be in the description below. But the best way to communicate with us is in LinkedIn. So see you in the next video.